Yes, I'm Zoe, and this is my supervisor, Deborah Andrews. So I'm from London South Bank University and been doing a PhD with the British Blinds and Shutters Association. So part of my supervisory teams includes a vast range of expertise. So Deborah is from School of Engineering and specialises in life cycle assessment. We also have Gordon Lowry and Kiko Giacometti from the School of Built Environment and Architecture. Liz Newton from the psychology background, so School of Applied Sciences. We've also been supported with Luigi, who I spelled his name wrong, that's awful, who's a master's student from Building Services, who supported us with the modelling side. And we also had the further help of Dr. Isa Chad. And then obviously Andrew and Dave have been invaluable to the research going forward. So, overheating in homes. Most people don't think it's happening in the UK, but it is. We've got the proof. There's been an increase in news articles documenting it. Professor Lomas from Loughborough University, who's been producing a large amount of documentation, academic literature, and reviewing it to show that there is an increase in trends in overheating in the UK. And with this, we have a large amount of literature also addressing particular scenarios. So we have evidence from BRE, overheating in dwellings, and how we should evaluate it. We have assessments from architecture saying that shading can reduce the effects of overheating. We also have papers from, where else we got? Zero Carbon Hub in the UK, and obviously across government. So to put this in perspective, I think the largest notable heat wave we had was in 2003. I think across Europe we all had a heat wave, and it was documented in the UK that there was an additional 2,000 deaths due to this heat wave. So in the UK, it has also now been picked up by the Climate Change Risk Assessment, where they've actually said that overheating is as big a problem as flooding in the UK. So the reason this is, and why this is occurring, is that in the UK, they say that people lack a basic understanding of the risk to health from indoor high temperatures, and they're unlikely and less likely to take measures to protect themselves. They've also said that it's not limited to South England. There's this myth that it's just the south of England that seems to overheat, but it's just simply not true. There is also evidence that newer homes are of greater risk. So we have issues with our building standards that they're not taking into account solar gains. So before I drag on and keep going on about overheating, I think it's important that we all know what overheating is and how it's quantified. So the term overheating in post-occupancy evaluations is not really defined very well. But in standards for building modelers, and building designers, it's in the UK, CIBSE Guide A is where we look for our information, ASHRAE Standard 55 and BSEN 15251 identify overheating as operative temperatures that exceed 23 to 25 degrees in summer, temperatures in winter that are below 17 to 19 degrees, and then so this is the temperatures for our buildings, but for our health, World Health Organization say that we should be within 18 to 24 Celsius air temperature, and those more vulnerable should be maintained at a temperature of 20 Celsius. So there's quite a big disparity. So we've got World Health Organization saying air temperature is the key thing, and we also have the buildings where they look at operative temperature. And operative temperature is a simplified measure of measuring human thermal comfort. So it encompasses air temperature, mean radiant temperature, which is the big one, which is not often picked up by air temperature, and airspeed as well. So it's a combination of them both. And how we measure this, we still haven't got very far with technology. We do have automated logging systems of this, but how we evaluate it, and a quick way to measure, is literally putting a thermometer in a black globe and putting a bit of blue tack around it so there's a seal. So this is what we did. So a little bit, I think I've touched on some of the reasons why overheating is happening. But in the UK, so we're building these buildings because it's obviously very cold in the UK, and that's always is a big issue. But we've increased insulation and reduced ventilation in our buildings quite drastically. So there's been a 23% reduction in heat loss since 1970. And alongside this, urbanisation in our cities. More people, more heat. And with this, so there's two images here of London, and you can see the buildings have all got a lot taller. So heat rises. And with the design of these buildings, they're also being designed so they're single aspect. So we only have one window on one side of the building. And there's no way to cross-ventilate the building to improve cooling. So I also touched upon, so culturally in the UK, our designers are not very aware that our buildings overheat. It's obviously common that it rains. And then we have also behavioural aspects. So climate change, the UK Climate Change Report picked this up, that we simply don't know when to operate shading. I think in the rest of Europe, you do it very well. We have external shading at least, where in the UK, unfortunately, our windows open outwards. So this is a big barrier. And it's also a common issue in America as well. So I also said it is not just a South England problem. So this paper by Professor Lomas, I won't go into too much detail, but he pinpointed a large range of studies that showed not only in new builds, in retrofits and existing dwellings, they are overheating. So we looked at, so the stats on here represent what rooms are overheating. So we have, in new builds, 25% of bedrooms were overheating for 3 to 9 months of the year as well. So it's not just in summer. So throughout the year, we're not considering these solar gains that are coming into our buildings. So there's a little rundown on how we can prevent it. So improvement in building regulations, so to consider solar gains and ventilation. There needs to be a clearer procedure on how to monitor overheating and a definition of what overheating is, especially when it comes to post-occupancy evaluation, which rarely happens. We need to produce more real-life studies and then be able to compare them to model scenarios and work out what's going wrong to improve this performance gap that we have. And education. Something we've definitely touched on today is that education is a great benefit. So communicating with the users how to use shading, when they should be using it, particularly when our homes, when we're at work, they're unoccupied. So if they close their blinds or shutters, then it is likely that they will be less hot when they get back. So after all that information, after reviewing all this information, we got the opportunity to monitor a block of flats in Camden, London. So we had full reign of this building. It was empty. The occupiers, the construction workers were actually, they were working on the project and they realised that they had an issue with overheating. In fact, in the flats at the top of the building, you can see that there's very heavily glazed rooms. So these were 2 apartments and they had air conditioning units in. But what they were actually finding is that they were having issues with the flooring actually staying down. So they wanted to turn the air conditioning unit off, but they couldn't because there was issues with the floor peeling up. In addition to this, in the apartments that we were actually reviewing, they noticed a strong smell of sewage in the drains. And this was because the water pipes had all dried up in the system. So what we set out to do was simply go into the building, start monitoring and compare a room without a blind to a room with a blind. So we went all out on this, even though maybe a bit crudely with some of our sensors. So we took external measures, air temperature and lux levels, and then internally we monitored operative temperatures, glazing surface temperature, lux levels, internal air temperatures, mullion surfaces, and also blind fabric surface temperatures, to just try and find out what was going on, how far we were getting with this. So here's a kind of a layout of one of the flats. So we had 2 of these flats that are identical. We put sensors relatively similar, so in a similar position between the two rooms, so in the centre of the room. The lounge space, so this space here, was shaded, so we kept the blind closed throughout the study. And we kept the bedroom doors closed as well throughout the study. And as you probably noticed, it's very heavily glazed. So we had a window area that was 3.2 by 1.85. And if you notice, the openable areas are very small. In fact, this top one here, which I still can't reach, I couldn't reach in the flat, so I wouldn't have been able to open it. We were actually having to get a stool and go up and open it. So they were top swung windows, so also the extent that they actually opened wasn't very far. And with this, so we wanted to find out, obviously, the G value in this instance, because we want to look at overheating, and we weren't able to obtain that from the design spec, but we were able to obtain a U value. So we tested sporadically these blind systems. The products we tested were external metal Venetian blind, an external fabric blind, an internal reflective screen blind, an internal screen blind, and then we had our internal metal Venetian blind, and we had a no blind room, which was our control room. So it was important to measure one versus the other. So we consistently had a control room. Throughout this study, we had 7 people hired. My poor students and interns, they didn't fare well with this monitoring, mainly because we had to climb so many stairs.
They died of dehydration.
Yeah, they weren't happy, especially the first day. Like, a couple of them came out in trousers, and they were like, yep, shorts. And also it really smelled. Fantastic. So we worked out 90,200 stairs in the time, because we had to keep going from ground floor outside, taking a measurement, going up to the 2nd floor, then to the 3rd floor, and then back down again. So we collated a large amount of data, so we collected measurements across 20 days. I think it ended up being whittled down to 16 days that were usable, because we had issues with builders coming around and closing the windows when we didn't want them to be closed, and issues like that. But to conduct this study, we had to create an occupancy profile. So what we suggested is we only were able to get access to the building between 8 and 4 o'clock, because they wanted to lock up and go home. So what we did is we utilised the use of nighttime ventilation. So from 4 o'clock till 8 a.m. the following day, we had the windows open. So overnight, you would open them all up. And then during the day, they would be closed, as if you would go to work, lock up, especially in North London, shut all the windows, and then we took measurements from 8 o'clock till 4 p.m. And this is kind of a little review of the results. So here we have our external temperatures. So we had a nice broad range. So this monitoring took place between, August and October. We had 5 days where the temperatures were between 15.3 and 20 Celsius. We had 5 days where they were between 20 and 25. And then we had 6 days where they were 25 to 34.2, which was our max. So we had a nice even distribution, more or less, of external conditions. So we then look at the extent. So throughout those days, we got to 47.5 Celsius internal temperature. So this is operative temperature, again, considering solar radiation. And then with internal blinds, kind of categorise these, and it dropped down to, I think the maximum was 34 Celsius. So an incremental drop of just over 10 Celsius, I think, yeah. And then for our externals, they performed the best, and the maximum temperature we got inside was 28 Celsius. So bearing in mind that the recommended operative temperature for bedrooms is between 23 and 25, we're well above, but at least shading has helped. So,
Can I ask you?
Yeah.
I mean, if the air conditioning was present, the way I understood when I heard about it was that if it goes 47, the aircon cannot manage.
In these flats, there was no air conditioning. It was just sorry, I didn't mean to confuse you, in those top flats. But the ones we were monitoring, they were supposed to be naturally ventilated.
Okay.
Only. They were only supposed to be naturally ventilated, and yet they were getting to these temperatures.
Is that window then? Is that window in the
Yeah. So we're just opening those 2 windows overnight, and then coming in, closing them as someone would go to work at 8 o'clock in the morning. They would wake up, get changed, close the windows, go to work, come back, and see what the temperatures are like.
Okay. Right.
Yeah, so we reached 47.5 Celsius. And funnily enough, Death Valley in California has a mean radiant temperature of 47.5 Celsius. This is a nice anecdote that Andrew found out. And the thing about Death Valley, no one lives there. Yeah. So we now come to the kind of, let's get some stats behind this and try and do a comparison. So what we looked at was comparing the range in operative temperature, so from the start of the day to the end of the day. And we compared those ranges in temperature between no blind rooms and internal blind rooms. So then we can work out a comparison of, compare a no blind room to an internal blind room, a room with an internal blind, a no blind room with a room that's got an external blind, and look at that difference. We looked at our 2080 future weather climate data, and Luigi, our master student, he did a review of all the data, found the hottest day, and then did a comparison. So I think I've got a pointer on this. Yeah. So here we have our real world operative temperatures where we hit the 47.5 Celsius. And somewhere here, yep. And this is our simulated 2080s data. So you can see, so the reason it cuts off here is because we only monitored till 4 o'clock, where the simulated data we could do the whole day. And we can see there's a big difference, a big disparity. We are peaking quite high here. And then we also obviously compared our external air temperature, so our real world was a lot lower than what would be simulated in 2080. So it's interesting to see that there's such a disparity between what's happening inside. So we then took this and did a comparison, and then we looked at the in both the real world scenario, so from here, in both the real world scenario, so if we compare, hang on, bear with me a second. So here we have the data for the real world case study, and we see, again, it peaks. We had a peak on this day, and then we compare it against the simulation, which is this one here with no blind, which is the 2080s data. We can again see that there's a big difference in how the day progresses, how the temperatures progress through the day internally. So we see that there's a 6-degree difference here between with a blind and without a blind. And in the simulation, we only see a 1.17 degree difference. And this is the issue that we're trying to investigate more, is to find out why there is such a big disparity. So so it was important that obviously we got a master student to model this. We then got his model quality assessed or quality assured by the National Energy Foundation. And they came back and said his model is fine. We can't see, there are a few issues that pinged up, but nothing that should really harm the output that we got from the simulation. So we concluded that the current modelling of passive shading intervention indicates that they have a minor impact on the indoor environment, which differs from the real world environmental data collected. The building software first omitted the solar heat gains, and particularly during extreme weather events, and the subsequent mitigation effect of the mitigation effect of the blinds, which hides the true value of what shading does. So there's also within this is part of a much larger thesis, but also within Luigi's evaluation of this particular software, he noticed an evident gap between current manufacturer product data and the inputs for this simulation tool. There's a big disparity, and their guidance does not match with what we produce and the rest of the industry produces and uses in other simulation tools. So there needs to be further longitudinal studies of real-world data and comparative simulations to reduce that performance gap. So there's still a lot of work to be done, and we know we have just simulated one tool. It's one of the biggest tools that is used across Europe. So we presented this at CIBSE last week. So CIBSE is the Chartered Institute of Building Services. So we put a paper together and did a presentation. It was very interesting. We had, I think, both sides, some in support and some going, oh no, you've definitely got that wrong. But it's created a snowball effect and opened a conversation, and that's the important thing, so that we can all discuss what is going on with this software, this particular software. The software itself is a black box model, and it is the big disadvantage with black box simulations. You can't unpick and you can't look at the equations behind it. So we really have no idea what it's doing. But the fact is, we've opened this dialogue and we're starting to get comments back and looking at it further. So what's next? So there's lots of other simulation softwares out there, and some of them we've been referred and said, oh, have you tried it in this? Have you tried it in this? So this is the next step. We've got a new PhD student, Bahareh Salihi. Yeah, pronouncing that roughly. She's literally only just started in the last month, so she's doing her literature review at the moment. So she's going to start taking on some of these software systems and looking into these differences. But we've also got the support from Lawrence Berkeley National Lab. They're having a look at the Energy Plus side at the moment for us. So hopefully we can find a resolution to this issue. Thank you very much for listening.